Again, we're back to this image where we have depolarization, and specifically, what are the events that we just mentioned that happen here at depolarization? What are the events that we just said happen with depolarization?
That sodium channels open and the cell rush in. Rushes in the cell becomes more positive.
Perfect. Sodium channels open. Both those gates are open, both the inactivation and the activation. Sodium rushes into the cell. Inside the cell is no longer -70, it starts to get more positive, and we generate an action potential. Now, these action potentials have the ability to communicate along the length of an axon. So you find action potential at the soma or the cell body, it's going to propagate all the way down the length of the axon, it's going to get to the axon terminal, and some sort of effect is going to happen depending on the location of this neuron. All right, it can be a postsynaptic neuron, and we have an effect at the effector organ. We're going to see that when we look at the autonomic nervous system. This could be a muscle, this could be the cardiac muscle, this could be a gland. Whatever that effect is, the neuron is really the vessel that's traveling, the stimulus is traveling along. Okay, so action potentials travel along the axon from the cell body all the way down to the axon terminal. Okay. It's important to understand that after this action potential is fired, we then repolarize the membrane here. And what were the events that were responsible for repolarization? What were the events that were responsible for repolarization?
The sodium channels close, potassium opens,
Right.
and then the cell starts to become more many.
Right, perfect. So the sodium channels close again, those inactivation gates are closed. We open up our voltage gated potassium channels, which again do not have that separate gates, right? And then we rapidly repolarize the membrane by introducing that rush of potassium back into the cell. The inside of the cell becomes more positive. All right. Let's look at the steps that are involved in firing an action potential here. Okay. Now we have two graphs on the right here, and if we look at the y-axis here, we have the membrane potential in the graph at the top, and the sodium and potassium movement or diffusion in the graph at the bottom, and on the x-axis we have time. Okay, so we're comparing these two things against time here. So the upshoot, which we mentioned here, when I say upshoot or upstroke, I'm really talking about this rapid depolarization here. This jump in the membrane potential from -70 all the way up to +30 millivolts. Okay, that is caused by the diffusion of sodium into the axon. Okay, and we can see that reflected down here with the opening of these sodium channels. Okay. So, to sort of bring all of this together, we start by having a few graded potentials. Let's say we have one graded potential, it's not quite as strong. We have another graded potential, that's not as strong either. We have a third graded potential, and these sort of combine or sum, and we get to threshold, we get to -55. We then have the opening of sodium gates, right? Voltage gated sodium channels. That causes sodium to then rush into the cell. Now remember, this is a positive feedback loop. Sodium begets more sodium, begets more sodium, and we have more sodium channels opening up here. Right? I want you guys to really understand what's meant by the positive feedback with the opening of these voltage-gated sodium channels. So sodium rushes into the cell, into the neuron, and this potentiates more sodium channels to open, and more sodium rushes in. This causes an overshoot of the membrane potential, and it gets all the way up to +30 millivolts. This is called depolarization. Right? This is the first phase that we sort of looked at. Right? This is your depolarization here. Let's move on. At +30 now, those sodium inactivation gates close, and then we have the opening up of the voltage-gated potassium channels. This is responsible for repolarizing the membrane. So I'll sort of point this out on those two graphs. So at this peak of positive 30, at this peak of positive 30, we then have closing of the inactivation gates or closing of those voltage gated sodium channels. Sodium is no longer rushing in. And what we have is opening of the potassium channels, and then potassium rushes out of the cell. That repolarizes the membrane. This is the negative feedback loop, okay? Why is this a negative feedback loop? Someone should be able to explain that. Why is this an example of negative feedback?
Is it bringing us closer to our resting membrane?
Perfect, thank you. We're bringing us closer, right back down to our resting membrane potential. And in this scenario, that would be an example of our set point, okay? So getting closer to this resting membrane potential is an example of that negative feedback that's happening. Okay. Now, this just really reiterates what we just spoke about. Excitable membranes, such as neurons, have an ability to fire an action potential, and then that can potentiate down the length of the axon, and this is used for communication. Okay. Just reiterating what we've been saying here, the purpose of an action potential, really. Okay, now this image just ties back in what we've talked about and the relationship here. So the opening of voltage gated sodium channels then potentiates sodium to diffuse into the cell. This causes more depolarization, which opens more voltage gated sodium channels. And this is your positive feedback loop here. We're getting further and further and further away from our set point here, until we get to what number, what figure, what voltage? Not negative 55, positive 30. All right, so this is going to move further and further away from the set point until we get to positive 30. At positive 30, what happens? Positive 30, we have repolarization, right? So then we have this purple box at the bottom where the potassium channels open, these voltage regulated potassium channels open. They cause potassium to diffuse out of the cell. That eventually repolarizes the membrane, and this turns off that signal. We get right back to our set point. And hence, this is an example of negative feedback, okay? So the membrane here goes from negative 70 all the way up to positive 30. And in repolarization, the membrane gets from positive 30 right back down to its set point of negative 70 millivolts. Okay.
So why do they use the word less depolarization? It's kind of confusing.
Less depolarization
It's right there.
is the same thing as repolarization. I don't know why this terminology was used, but it's the same thing. The membrane becomes more negative. Okay. All right, any questions so far? What questions do we have? Any questions?
If we have some time, if we go over that summation a little bit.
Okay, sure. Any other questions? Any immediate questions? Okay, so let's keep going here. Right, so just to review here, this is bringing us right back to what we talked about in Friday. At resting state, the membrane has a increased permeability for potassium versus sodium. So the membrane potential at rest more closely looks like, or more closely reflects, the equilibrium potential of potassium. Right? And we said this on Friday. So when the membrane potential moves closer to positive, when it's depolarized, it starts to look more like the equilibrium potential of sodium. Okay, so I'll say that in another way. At rest, the membrane potential looks more like the equilibrium potential for potassium, and that is because the membrane has an increased permeability for potassium. And permeability means that there are more potassium channels. And again, we're speaking about the leak ion channels, not the voltage gated channels. Whereas at rest, the membrane potential is very far from the equilibrium potential of sodium. Okay, and that's because there are less leak channels for sodium open. So if we look at this graph, which compared the action potential events to the membrane permeability, in blue we have the permeability for potassium, how it changes. In this purple, we have the permeability for sodium, and the red is the actual events of an action potential. So what we see is that during an action potential, the membrane potential is going to closely reflect the equilibrium potential for sodium. Can anyone explain why that is? Why does the membrane potential start to look more like sodium's equilibrium potential during an action potential?
Is that because more sodium's rushing in?
Right, perfect. More sodium is rushing in. We opened up more sodium channels. And I really want you to make that connection. The membrane permeability really is what's influencing the movement of ions. So the movement of ions, rather, is what's influencing the membrane permeability. And if we open up lots of sodium channels, the membrane potential will start to approach the equilibrium potential of that ion that's moving, that's in question. Alrighty, so opening up those sodium channels, sodium starts rushing in, and the membrane potential is approaching that sodium's equilibrium potential. Alrighty. Okay, any questions? Any questions? All right, let's keep going. Now, we depolarize the threshold. Again, using graded potential, so lots of little small changes or fluctuations in the membrane potential. Those are then summed, and we determine whether or not we get to threshold. If we did get to threshold, we spike an action potential, and then we repolarize back to normal. But the graded potentials are vital in determining whether or not we got to threshold. It's going to be very important. These graded potentials, these small changes in the membrane potential, will determine whether or not we get to that -55, which is our all or none reference point. Above -55, we're going all the way up to 30. There's no going back. Okay.
Do they get like added together or something? Or how
They do. Right, so let's go back. Let's go all the way back here. So they do get added together. So let's say we have a small bump in the membrane potential. Let's say it's about 10 or 15 millivolts here, right? From -70 to maybe -60 or -65. Then we get another one. These two will add onto each other or summate, and then we would have enough of an amplitude to generate an action potential, right? Because when you add this little blip with this little blip, you get to -55. Alrighty, and so summation is basically how these small graded potentials can generate enough strength to get to a threshold, and you can still have an action potential. So I'll say it this way. Action potentials are composed of many graded potentials that have summed together. But not all graded potentials are not action potentials. Does that make sense? The graded potentials are not action potentials, but action potentials are the summation of many graded potentials. Okay. All right. Any other questions on that? Okay, so we were going through the sequence of events here. I'm kind of getting, all right. So the next step we saw was the rapid opening of these sodium channels. And again, this is a regenerative mechanism. And regenerative mechanism means this was a positive feedback loop. This is going to continue to potentiate until we had that upshoot in the membrane potential. That is followed by the slow closing of sodium channels, right? The closing of those inactivation gates, followed by the opening of those potassium channels, which was the voltage-gated potassium channels. Potassium now washes out. This is the reason that an action potential does not get to sodium's equilibrium potential. Because we have that change, at positive 30 millivolts, we have that shift. We have the closing of the inactivation gates of sodium, closing of sodium gates, and then we have the opening of potassium channels. And so the membrane potential never fully gets all the way to positive 60, which is sodium's equilibrium potential. It only approaches sodium's equilibrium potential. That's very important. Okay, so we do not depolarize all the way to positive 60, but only to positive 30. Okay. Alrighty. Okay, so then the potassium channels remain open by beyond the resting membrane potential, and potassium continues to leave the cell. We hyperpolarize all the way back down, and we get close to the equilibrium potential of potassium, which is negative 94 millivolts. Okay, so these are the ending events of an action potential, basically. We repolarize the inside of the cell, we make it more negative again by kicking potassium out. Remember, potassium is a positively charged ion. If we kick it out, the inside gets more negative again, and the membrane potential then gets all the way down to the equilibrium potential for potassium, which is hyperpolarized. Okay, that's negative 94 millivolts. At this point, we have a refractory period. We have a refractory period where we cannot fire another action potential. Right? We'll talk more about that at the end, but just remember that. After we fire an action potential, there's a small refractory window where we cannot fire another action potential. Now, all of this is being kept in place. All of these gradients are being maintained by the presence of the sodium-potassium pump.